Our focus up to this point has been primarily on the study of natural numbers and their ratios, the rational numbers. If we view these numbers as the yin of number theory, here in the remaining lectures we study the yang, the more enigmatic, irrational numbers. These numbers, perhaps first discovered by the Pythagoreans, ran so counter to the original notion of number that many refused to accept them as actual numbers. Once humankind embraced these objects as numbers, the desire to understand their mysterious nature gave birth to an entirely new, uncharted branch of number theory. Here, we'll introduce the concept of irrationality, its early history, and some important examples, including the numbers pi, e, and the more mysterious gamma. After a brief overview of the decimal expansions of real numbers, we'll discover that the irrational numbers are precisely those decimal expansions whose endless screed of digits never settles down and never becomes periodic. This insight follows from the division algorithm we studied earlier together with the so-called pigeonhole principle. While these irrational numbers first appeared as strange and exotic to our ancient ancestors, we'll discover that these numbers, in fact, totally dominate the number theory landscape. Well, the Pythagoreans viewed the natural numbers as God-given numbers. These were the numbers of the gods. And they believed that one way to attain a closer relationship with the gods was through a deep understanding of the nuance of the God-given numbers, the natural numbers, in other words. The Pythagoreans also explored the ratios of natural numbers, but it's not clear that they actually considered these as numbers rather than just more as combinations of two numbers and not numbers in their own right. The Pythagoreans believed that all lengths of objects could be measured using either natural numbers, the God-given numbers, or ratios of natural numbers. This belief actually is connected with the idea of commensurability, in which the ratio of lengths of two objects equals a rational number. Well, if we adopt for the moment this Pythagorean mindset regarding lengths, then we'll run into some trouble when we consider the length of a diagonal of a unit square, a square where each side is length 1. So let's actually consider that. Let's consider a square having side lengths equal to 1 unit. If we draw a diagonal, then we see that the length of the diagonal is a number certainly larger than 1 and smaller than 2. And thus it can't be a natural number. Assuming the Pythagorean belief, we must conclude that this length is therefore a ratio of natural numbers. In other words, it must be a rational number. And let's just call it a over b for some natural numbers a and b. Well, we'll now see that this harmless seeming assumption will lead us to an impossibility. Something goes wrong. Applying the Pythagorean theorem to the right triangle we formed, we discover that the hypotenuse, which is a over b, the hypotenuse squared, a over b squared, equals one leg squared, which is 1 squared, plus the other leg squared, 1 squared. So 1 squared plus 1 squared equals a over b squared. In other words, a over b squared equals 2. Thus, in modern notation, we would have that a over b is the square root of 2, because a over b is some length, and so it would be the positive solution to that equation, which is the square root of 2. However, returning to the original equation, we conclude that a squared divided by b squared, that's a over b squared, is equal to 2. That's what we saw earlier. And if we now just multiply both sides by b squared, we would see that a squared equals 2 times b squared. Now, factoring these identical numbers into primes reveals something a little disturbing. On the one hand, the number of factors of 2 in the factorization of a squared is even. Now, why is that? Well, because we factor a into the product of primes, and then a squared is just another copy of all those primes. So it's almost like a Noah's Ark. Every prime appears in pairs, once with a and then again with a to generate a squared. So whatever number of 2's appear in a, we see the exact same number of 2's appearing in the factorization of a again. When we put them together, we'll see an even number of factors of 2 in a squared. While on the other hand, the number of factors of 2 in the factorization of 2b squared is going to be odd by the same reasoning. B squared alone will have an even number of factors of 2, but then we have that 2 multiple in front, and therefore we have an extra 2. So whatever even number we have, we add 1, which makes it odd. Well, this fact, the fact that on the one hand we have a number that has an even number of 2's in its factorization, and on the other hand that same number has an odd number of factors of 2, well, this actually contradicts the fundamental theorem of arithmetic that asserts that the factorization into primes is unique. So we can't have it both ways. Well, this contradiction reveals a logical fallacy. Thus, the Pythagorean assumption that all lengths are rational must be false. In other words, we've just proved for ourselves that the square root of 2 is an irrational number, a number that is not a ratio of natural numbers. Well, thus we discover that there are, in fact, numbers that are not ratios of integers, and so we come upon a fantastic discovery. In fact, this proof, which goes back to Euclid, is considered one of the most beautiful proofs in mathematics, since, in fact, the idea of the strategy is somewhat straightforward and elegant, even though to come up with the idea is daunting. The Pythagoreans didn't view these strange lengths as numbers, but did acknowledge that such strange lengths, even if they were not God-given numbers, did exist. It took hundreds, if not thousands of years for people to retrain their intuitive sense of number so as to embrace these irrational numbers as genuine numbers. Today, mathematicians and scientists view irrational numbers as real as the natural numbers. So we've come a long way. Now, we could actually adopt our argument that we just used to show that the square root of 2 is irrational to prove that both the golden ratio, 1 plus the square root of 5 over 2, and its cousin, its conjugate, 1 minus the square root of 5 over 2, are in fact both irrational numbers. Thus, we see that the golden ratio is another example of such an exotic irrational number. But moreover, if we now return to the famous Binet formula for the nth Fibonacci number we derived in lecture 6 for ourselves, remember this says that the Fibonacci numbers, which remember are 1, 1, 2, 3, 5, 8, we add 2 to get the next one. We add 2 previous numbers together to get the next one. Then we found the amazing Binet formula, which states that the nth Fibonacci number is equal to the golden ratio, phi raised to the n power, minus its conjugate raised to the n, all divided by the square root of 5. Well, now we could even be even more impressed by this amazing synergy between these irrational numbers. They come together and can be subtly combined to produce natural numbers in this very unexpected way, because of course the Fibonacci numbers are natural numbers. To discover another important example of an irrational number, we return to the idea of a logarithm, known as log. Now, the key phrase here to remember is the 5-word declaration that a log is an exponent. Now, there are many different types of logarithms, but here, when we say log, we mean log base 10. In other words, if we write log A equals B, then what does that mean? Well, a log equals an exponent. So B is the exponent I raise 10 to in order to get a. Or in other words, 10 to the b equals a. That's the identical statement as log of a equals b. Those two statements say the same thing, just looked at differently. So for example, log of 100 equals 2. Why? Well, because log is an exponent, so 2 is the exponent I have to raise 10 to in order to get 100. Well, we now claim that log of 2 is in fact an irrational number. Well, to establish this claim, let's call this number b. In other words, we'll say that log of 2 equals b. Well, we prove this assertion by contradiction. So we assume, contrary to what we hope to show, that b is a rational number. Let's call it r over s, for some natural numbers r and s. Well, given that log of 2 equals b, we know from our 5-word definition of log that 10 to the b power equals 2. In view of our assumption that b is rational, we see that 10 to the r over s power is equal to 2, which, if we raise both sides of this equation to the s power, is equivalent to 10 to the r equals 2 to the s. And remember here that r and s are natural numbers. Well, this equality is impossible in view, again, of the fundamental theorem of arithmetic. The prime factors on the right side consist solely of 2's. It's 2 to a power. While on the left side, we see the primes both 2 and 5 appearing because, of course, 10 is 2 times 5. Well, the same number cannot be factored in two different ways like this, and thus we arrive at a logical contradiction, a fallacy, if you will. Hence, our assumption must be false. In other words, log 2 must in fact be an irrational number. Now, I should caution you that this is a little bit tricky. And these little arguments are, in fact, subtle for establishing irrationality. And in particular, the act of actually producing proofs of irrationality for general, more complicated numbers is much, much more challenging. Well, to see the notion of irrationality in a different light, in a more modern light, let's return to decimal expansions. Well, just as we saw in Lecture 5 with the golden ratio, both the square root of 2 and log 2 can be expressed as decimal numbers. A calculator could actually reveal the first few decimal digits. For example, the square root of 2 begins 1.414213, and so on. And log 2 equals 0.301029996, and so on. It goes on. Let's just notice that it's not at all obvious how the digits continue. They look like a jumbled, chaotic mess. Numbers that possess a decimal expansion are actually called real numbers and can be viewed as points on a number line. Now, once we've marked the point 0 on a number line, every other point is then determined by a length, namely its distance from 0, understanding that we could also have a negative value as well. Thus, the real numbers can be thought of informally as all possible lengths of objects together with their negatives and 0. It's a straightforward task to find the decimal expansion of a rational number. We merely apply long division, or said in the language of number theory, we repeatedly apply the division algorithm. If we consider, for example, the rational number 1/7 and perform long division, and just keep track of the remainders that we see as we go through that process, then the remainders we'd see would be 1, 3, 2, 6, 4, 5, and then actually we would return back to 1, and then see 3, 2, 6, 4, 5, and so on. So these remainders, in fact, must eventually repeat. And we can actually see why this is true for ourselves. Why? Well, because in fact, the number of choices for the remainder is a finite list. When we are looking at dividing by 7, for example, we see the remainders have 7 possibilities: 0, 1, 2, 3, 4, 5, or 6. So if I continue to look at these division issues and look at the remainders, at some point I have to hit a remainder I've already seen. Well, the fact that we must return to a previously seen remainder is an illustration of the pigeonhole principle. The pigeonhole principle asserts that if I have a whole bunch of pigeons and one fewer pigeonholes, and if I'm supposed to put in a pigeon into a pigeonhole, then no matter how I try, there will always exist a hole that consists of more than one pigeon. So we have to put in some extra pigeons into some hole at the very least. This is exactly the same process that we're using with the remainders, because you see, I only have 1 through 6, and if I keep picking numbers from 1 to 6, within 7 tries, if not before, I have to hit on a number I've already seen. Well, given this repeating remainder phenomenon, we see that the decimal expansion must eventually become periodic. And this argument actually holds for the decimal expansion for any rational number. Thus, every rational number has a decimal expansion that eventually becomes periodic. Even the decimal expansion for a half eventually repeats. We'd see 0.500000000 forever, an endless list of zeros that repeats. It's periodic. Now, interestingly enough, the converse is also true. If a decimal expansion for a real number is eventually periodic, then it must be a fraction, a ratio of 2 integers. For example, if we consider 0.66666 forever, then we know that it equals the rational number 2/3. We've seen that for ourselves, and that's just one example. Well, from this discussion, we conclude that a real number is a rational number if and only if its decimal expansion is eventually periodic. If we stand this result on its head, we discover that a real number is irrational if and only if its decimal expansion is never eventually periodic. In other words, its decimal expansion never repeats endlessly. Well, thus we can now immediately conclude something interesting about the decimal expansions for the golden ratio, square root of 2, and even log 2. None of their decimal expansions will ever become periodic. Well, in fact, if you think about that, that's a really fantastic conclusion, because we don't know all those digits as you look down that endless run of digits for any of these irrational numbers, and yet we can say something definitive about that chaotic list. It will never become periodic. Even though we don't know the precise digits themselves all the way out, we can say something about the collective whole, the power of number theory. In fact, we can actually apply this proposition to generate other irrational numbers in terms of their decimal expansions. For example, let's consider the decimal number 0.101000100010001, and so on, where every time through I add an extra zero sandwiched between those two ones, and then I keep having an ever-growing list of zeros. Well, this number can't be periodic because we see that the number of zeros between consecutive ones is ever growing. Thus, the decimal expansion provides us with a modern means of demonstrating that irrational numbers do in fact exist, although we saw the more ancient proofs looking at square root of 2. Now, the decimal expansions allow us to make further insights into the nature of numbers. We've seen that non-repeating decimal numbers are precisely the irrational numbers, and the decimal numbers that eventually become periodic, eventually repeat, are the rational ones. Of course, we're more familiar with the rational numbers, and thus the irrational numbers appear to us as exotic and exceptional. But are they really? If we were to pick a decimal number out at random, what are the chances that it would be a rational number? Well, we can, how do you actually go about doing this? I mean, how do you pick a point on the real number line at random? Well, we could pick a decimal number at random by randomly generating the infinitely long list of digits in its decimal expansion. And we could actually do this by rolling a fair die. So we could take a fair 10-sided die. You don't see these every day, but there's 10 sides. Fair means that every side is just as likely to come up as any other side. 1 in 10 shot. You can see all the odd ones are here. 1, 7, 3, 5, 9, and then here we see 0, 4, 6, 2, 8, and so on. And now, if you just roll this die forever, then in fact we could generate a random real number. And so let's actually try it right now. So if I try it right now, and I'll read them off to you, you can't see, but, and wait, and I want this number to be, just for fun, between 0 and 1, between 0 and 1. So we'll start with 0 point, and then here we go. First digit is an 8. Then we see a 9. Then I see another 9. Then I see a 5. Then I see a 9. Well, what are the chances that if we keep doing this, we would see 959, 959, 959 repeated forever? Well, if this is really a fair 10-sided die, then we would expect each side to come up with the same frequency if we keep doing this again and again. So seeing a 9, seeing a 5, 9, 5, 9, 5, 9 forever would be exceptionally unusual. You'd be shocked if you saw this in Vegas. And so, in fact, what we see here is that it's highly unlikely, in fact, nearly impossible, to produce a random number that is, in fact, a rational number. Thus, mathematically speaking, the probability that a random decimal number is rational actually equals 0%. And the probability that a random decimal number is irrational equals 100%. Now, that seems to be a little bit vexing because on the one hand, you say, wait a minute, but of course the rational numbers do exist, so couldn't I accidentally hit upon one? Well, not by accident. One way to visualize this is to go out one evening and look up into the dark sky. And there you'll see, on a really clear night, you'll see the stars sparkling. But what you're looking at primarily is the dark canvas of the sky. And so you see these stars because they're so exceptional, they're so unusual, they stick out because they're being illuminated. Well, if you were to close your eyes and just pick a particular point in space without looking, what do you think the chances are that you would be pointing exactly at one of these rare stars, these points of light? Well, the answer is, of course, 0. You'll most likely be pointing to the blackness of the sky. Well, that's the way to think about this synergy between rational and irrational numbers. They exist, they're stars, but you'll never point to one by accident. Well, this mathematical reality really forces us to retrain our intuition and refine our view of nature. In reality, the familiar rational numbers are in fact the exception, and the seemingly exotic irrational numbers are really the norm. And this is a great surprise and a great moment to celebrate surprises. A surprise, of course, is a realization that our intuition runs counter to reality. It's a great chance for us to retrain our thinking. Now, this surprising realization is, in fact, a wonderful opportunity to celebrate the power of number theory. This also challenges our sense of what is commonplace and what is genuinely rare. Well, let's now highlight some very famous real numbers, and of course, we begin with the ever-present pi. The number pi is an ancient constant that's defined to be equal to the ratio of the circumference of a circle to its diameter. Numerically, we can actually compute pi, and we would see it's 3.14159, and it goes on from there. The number pi is a very complicated number, and thus there are no easy ways of expressing it. Now, there are many complicated ways, including an amazing infinite series, a sum of infinitely many numbers, and that endless sum is given by pi equals 4. Now, 4 is a little bit bigger than pi, so we've got to subtract something. So we subtract 4/3, but that's a little bit too small. So now we add 4/5, and then we subtract 4/7, then we add 4/9, then we subtract 4/11, and you can see the pattern. We alternate between adding and subtracting. We have 4 divided by the odd numbers. If we do that forever, endlessly, that sum difference equals pi. Well, to establish that this infinite series actually does equal pi actually requires techniques from calculus, which we won't consider here. The richness of pi can also be seen by the property that pi is, in fact, an irrational number. Now, this deep result, while extremely technically complicated, actually follows the same logical reasoning as our previous irrationality proofs. We assume that pi is rational and deduce a contradiction. Well, we now turn to the more modern constant named e. The number e, known as Euler's constant, is a number that helps us understand growth and change, whether it's in the context of the reproduction of living cells, the decay of radioactive substances, or the compounding of our retirement nest eggs. In fact, it's one of the most important numbers from calculus. Numerically, it's given by 2.71828818, and it goes on, so on. The number e can also be expressed as an attractive infinite series, again from calculus. E actually equals 1 plus a half plus 1 over 3 times 2 plus 1 over 4 times 3 times 2 plus 1 over 5 times 4 times 3 times 2, and so on. The pattern continues with the denominators getting larger and larger. Well, using this endless sum, it can actually be shown that e is also an irrational number, although, again, we won't bother with the details right now. Well, I want to close this lecture by introducing 2 mysterious constants from number theory that we probably haven't seen yet. In our discussion of prime numbers in lectures 8 and 9, we came upon the Riemann zeta function, which we called zeta of s, and it equals the sum 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus 1 over 5 to the s, and so on. And as we saw, this infinite series played a key role in the prime number theorem and is the centerpiece of the famous Riemann hypothesis, one of the most famous and important open questions in all of mathematics. In our discussion of square-free natural numbers from lecture 8, we came upon the number zeta of 2, or 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on, which we asserted equals pi squared divided by 6. Well, this famous number 2 can be shown to be irrational. But what about zeta of 3? That would be 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed, 1 over 5 cubed, all added together. Well, is this number irrational as well? Well, while there is no known nice closed formula for this number, as we have for a zeta of 2, pi squared over 6, we do know something about its value. In 1977, the French mathematician Roger Appéré proved that this number is in fact irrational. And his argument was extremely complicated and ingenious and involved all these things that we've seen throughout the course, including recurrence sequences. Thus, this series is now known as Apéré's number. He was quite a character, by the way. There's a story about him working through the proof of this irrationality, sitting back of a conference in like a theater type setting, and all of a sudden you heard the clanking of a bottle that fell and started to roll down the aisles, which was the housing one of his adult beverages that he was enjoying. So he was quite a fun-loving mathematician as well as a great creative scientist. Well, finally, we recall the harmonic series from lecture 8 given by 1 plus a half plus a third plus a fourth plus a fifth, and so on. In that lecture, we proved that this series diverges to infinity and wasn't a number. Well, even though the unending sum equals infinity, it grows very slowly. As we add more and more terms, very, very slowly, it gradually moves to infinity. In fact, it grows at the same rate as the natural logarithm ln of n. And we actually studied the natural logarithm in lecture 9. More precisely, if we consider the difference of 1 plus half plus a third all the way out to 1 over n, and then we subtract off the natural log of n, look at the difference of those two quantities, then as n gets larger and larger, this difference actually approaches a fixed number. And this number is denoted by gamma. And the first few decimal digits of the expansion of gamma actually have been computed, and it's known that gamma, in fact, equals 0.577215, and so on. However, no one has been able to prove that this number is irrational. This remains an extremely difficult open question. In fact, David Hilbert said that proving the irrationality of gamma appears to be totally unattainable. It's also said that G.H. Hardy offered to give up his very prestigious chair at Oxford to anyone who was able to prove that gamma is, in fact, irrational. Well, he didn't have to do that. Well, here's a fun fact about gamma. It's known that if gamma were to be a rational number, say a over b, then the denominator b must be pretty big. In fact, it's got to be a lot bigger than 10 raised to the power 240,000. That's 1 with 240,000 zeros, and the denominator would exceed that. So you can see it's not looking good for gamma. Anyway, open questions abound in the mysterious and beautiful theory of irrationality, a world that we have now just entered.